Every photograph you've seen of the object sitting at the center of our galaxy might be showing you the wrong thing entirely. Not a black hole, not even close. In 2022, the Event Horizon Telescope released the first ever image of Sagittarius A, the supermassive object anchoring the Milky Way, and the world called it proof. Scientists, more carefully, called it consistent. Those are not the same word. Because right now, no one has ever directly proven that Sagittarius A times actually contains an event horizon, the one feature that would make it a true black hole. And a small group of physicists now argue it might not need one at all. Their alternative isn't science fiction. It's built from real orbital data, real telescope images, and a particle most of us have never heard of. Here's the uncomfortable truth buried under decades of confident headlines. Every single piece of evidence for a black hole at the galactic center is indirect. For nearly 30 years, astronomers have tracked the orbits of stars near the center of the Milky Way, most famously a star called S2, which whips around an invisible point of gravity at speeds exceeding 7,000 kilometers per second, closer and faster than anything should be able to survive. By watching how that orbit bends and accelerates, scientists calculated the mass it must be circling, roughly 4 million times the mass of our Sun, somehow packed into a region smaller than the distance between the Sun and Mercury. That calculation earned the 2020 Nobel Prize in Physics. It is, without question, the strongest evidence we have for something extraordinarily massive and extraordinarily compact sitting at the heart of our galaxy. But notice what it actually proves. An enormous, invisible mass exists. It does not prove what that mass is made of. Then came 2022, and the image that seemed to settle the debate for good, the Event Horizon Telescope's picture of Sagittarius A, a glowing ring of superheated plasma wrapped around a dark central shadow. It was stunning. It was real. But a shadow isn't a fingerprint. A shadow is simply the absence of light bending around something massive enough to trap it, and there is more than one type of object that can produce that exact effect. For nearly a century, the black hole explanation has dominated not because it was definitively proven, but because it was the simplest model that fit the data we had. Simplicity is a useful guide in science. It has never been the same thing as certainty. In recent research, a small group of physicists proposed something that sounds almost heretical. Sagittarius A times might not be a black hole at all. Instead, it could be an ultra-dense, self-gravitating core made of fermionic dark matter, a theoretical class of particle that behaves a little like the neutron-degenerate matter packed inside a neutron star, except built from a substance that barely interacts with anything in the universe except gravity itself. For most of modern astrophysics, dark matter has been treated as something almost featureless, an invisible fog spread thinly across galaxies, detectable only through its gravitational pull and nothing else. This new model challenges that picture. It suggests dark matter, under the right conditions, can behave far more like ordinary matter does when it collapses into stars, clumping, concentrating, and packing together under its own gravity until it forms something dense enough to dominate a small region of space. Run that process at galactic scale, and the math produces something remarkable. Fermionic dark matter particles, compressed tightly enough by their own gravitational pull, can form a compact central core, while the rest of the same dark matter population spreads outward into the enormous, diffuse halo that envelops the entire Milky Way. In this model, the object we call Sagittarius A times and the dark matter halo surrounding our entire galaxy aren't two separate structures that happen to share a neighborhood. They're the same continuous structure, the same substance, just measured at two wildly different scales, dense and compact at the center, thin and sprawling at the edges, governed by one unified set of physics from the core all the way out to the galactic rim. What makes this idea genuinely difficult to dismiss is exactly what the math is capable of reproducing. When researchers modeled this dark matter core and ran the numbers against real observational data, they found it could match the orbital motion of stars like S2 near the galactic center just as precisely as a standard black hole model does. That alone would be notable. But the model goes further, reproducing something far more demanding. the shape and shadow captured in that 2022 Event Horizon Telescope image. A sufficiently dense, sufficiently compact fermionic core can bend surrounding light and produce a dark central silhouette, nearly indistinguishable from an actual event horizon without ever forming one. And the same underlying framework doesn't stop at the galactic center. It extends outward to explain the broader structure of the Milky Way's dark matter halo, connecting the smallest scale we can observe, a region barely larger than our solar system, to the largest scale in the galaxy, all governed by one continuous model instead of two unrelated explanations bolted together. It doesn't end there either. ESA's Gaia mission has spent close to a decade precisely mapping the position and motion of well over 1 billion stars across the Milky Way. And some of that motion doesn't sit comfortably with standard galactic rotation models. Subtle irregularities and asymmetries that conventional dark matter distributions struggle to fully explain. A more structured core and halo dark matter model offers a possible piece of that puzzle. And separately, billions of years away from anything happening in our own galaxy, the James Webb Space Telescope keeps discovering something that shouldn't exist. Galaxies that appear far too massive and far too mature, observed at a point in cosmic history just a few 100 million years after the Big Bang. Not nearly enough time for them to have grown that large under standard models of galaxy formation. A dark matter framework that behaves differently and collapses faster at galactic centers could offer a partial explanation for how that early growth happened so quickly. 3 separate mysteries sitting in 3 completely different corners of astrophysics. One model potentially threading a line through all of them. Before this starts sounding like a settled case, here's the necessary reality check. The overwhelming majority of the scientific community still favors the standard black hole explanation, and for legitimate reasons. General relativity has survived over a century of the most rigorous tests physicists could devise, from gravitational lensing to gravitational waves to the precise orbits of stars at the galactic center. The black hole model is simpler, it requires fewer assumptions, and critically, it doesn't depend on the existence of a dark matter particle that has never once been directly detected in any laboratory on Earth, despite decades of dedicated searching. The honest, unglamorous truth sitting underneath all of this is that current instruments simply cannot tell these two models apart. Both reproduce the orbital data from stars like S2. Both can produce a central shadow closely matching the Event Horizon Telescope's image. At the resolution available to us right now, a genuine black hole and a sufficiently dense fermionic dark matter core look almost identical from 26,000 light years away. Closing that gap is exactly what the next generation of research is aiming for. Higher resolution telescopes capable of resolving finer structure near the galactic center, and dedicated dark matter detection experiments searching directly for the particle this entire theory depends on. If that particle is ever isolated in a lab, or if a future image reveals internal structure that no true event horizon could ever produce, the question gets answered. Until one of those things happens, this remains a genuinely, legitimately open scientific question. Not settled, not solved, and not going away anytime soon. Step back from the technical details, and the real significance of this idea has nothing to do with whether Sagittarius A star personally turns out to be a black hole or a dark matter core. It's the possibility buried underneath that question that 2 of the largest unsolved problems in modern physics, the true nature of dark matter and the true identity of the object anchoring our entire galaxy, might not be 2 separate mysteries running on parallel tracks at all. They might be the exact same question asked from 2 different distances. For decades, dark matter has been treated almost like invisible scaffolding, something inferred purely from its gravitational influence on the stars and galaxies around it, and nothing more. This theory suggests it might be capable of something far more dramatic than scaffolding, collapsing into ultra-dense structures, extreme enough to mimic the most violent objects we know of in the universe, all without ever crossing the threshold into an actual event horizon. We don't have the final answer yet. Nobody does, not really. But that's the part worth sitting with for a second. Somewhere at the exact center of our galaxy, 26,000 light years from where you're sitting right now, there's an object so extreme that even our best telescopes, our best mathematics, and our best physicists still can't agree on what it actually is. The Milky Way has been keeping that secret since before our species existed, and for now, it's still keeping it. If this kind of deep, evidence-driven space mystery is exactly what you come here for, subscribe, because we're tracking every major update on Sagittarius A times and the search for dark matter as the data comes in. Drop a comment and tell us where you land black hole or dark matter core. And if this changed the way you think about the center of our own galaxy, send it to someone who needs to hear it too. We'll see you in the next one.